Okay, in this lecture we are going to discuss about the biaxial stress system. The biaxial stress system means there's only x and y direction stresses. That means all the stresses acting on an element we can represent on a two-dimensional plane. Okay, including the shearing stress, including the normal stresses. That means z direction stress are vanishes. So then these kind of systems are called the biaxial stress system. There's a lot of biaxial stress system. One of the very good example for the biaxial stress system, thin wall pressure vessel. Okay, when the thin wall pressure vessel is subjected to a internal gauge pressure, its outer shell is subjected to a biaxial stresses, the circumferential stress and also the longitudinal stress. Okay, there's a lot of biaxial stress system. In this lecture also we are discussing the Poisson effect and also sign convention when marking the stresses on a biaxial stress system, and also we are discussing stress acting on a inclined plane also. Okay, so let's continue to today's lecture. In this topic we are going to discuss about the biaxial stress system. Well, let me define what is this biaxial stress system. If all the stresses acting on an element, if you can represent it on a two-dimensional plane, we can represent it as we can call it as a biaxial stress system. That means, for example, if you take a certain element, if all the stresses acting on this element, if you can represent on a two-dimensional plane, for example, the normal stresses in x direction, let's define the coordinate axes as x and the y. The normal stress acting on x direction and also the normal stress acting in y direction, and also the shearing stresses acting tau xy, tau yx. You can see all the stresses acting on this element we can represent on a two-dimensional plane, no? Xy two-dimensional plane. These kind of stress systems are called biaxial stress system. Okay. Then what are the example? What are the example for this biaxial stress system? For example, let's take this kind of sheet. Let's take this kind of sheet. Let's take this sheet metal. We are applying this kind of distributed forces in this in this direction, and also we are applying forces in this direction. Let's take the coordinate system x and the y. Okay, f1, f1, f2, f2. Okay, you can see this sheet metal is subjected to a f1 and f2 distributed forces. Okay, then if you take a certain element from this sheet metal, I'm going to take this kind of a element, infinitely small element. Okay, then all the stresses acting on this element we can represent on a two-dimensional plane. That means infinitely small stress element in this direction sigma x, in this direction sigma y, something like that. Okay, on a all the stresses acting on this element, considering element, we can represent on a two-dimensional plane. That's called we call biaxial stress system. That means this sheet metal subjected to a biaxial stress system. Okay, another example, if you take a pressure vessel, I think you all know what is the pressure vessel. The pressure vessel means the pressurized fluid containers are called the pressure vessels. The fluid containers are called the pressure vessels. Okay, gas tank, gas storage tank, fluid storage tanks, acetylene cylinders, oxygen cylinders. These are called pressure vessels. Normally its internal pressure is greater than the atmospheric pressure. The PI is greater than the PO. Then this is manufactured using the sheet metals, thin sheet metals. Okay, these are manufactured by thin sheet metals, thickness is, let's take the thickness as t, the internal diameter as capital D. Okay, compared to the capital D, t is very small. Compared to the capital D, t is very small for thin wall pressure vessels. Okay, so then if you take when this pressure vessel subjected to internal gauge pressure, its surface, its shell is subjected to biaxial stress system. That means if you take a certain element from the shell of the pressure vessel, okay, the element from the shell of the pressure vessel, the stress acting on this point, okay, point element, that means infinitely small stress element, we can represent on a two-dimensional plane. Okay, this is called sigma L. Okay, sigma L. This is called sigma C. This is called sigma C. This is called longitudinal stress. Stress acting in longitudinal direction. Stress acting in sigma C is called circumferential stress. Stress acting in a circumferential direction. Okay, this is another very good example of the biaxial stress system. When what are the situations for biaxial stress system? I think you all got a clear idea what is meant by the biaxial stress system. In today's lecture, we are in detail discuss how to analyze this kind of biaxial stress system and to find the then we are moved to the in next topic we are going to move to the finding the principal stresses for this kind of biaxial stress system. Okay, then before going to the then next subtopic I am going to discuss the Poisson effect. Poisson effect. Okay. Then what is meant by this Poisson effect? With related to the biaxial stress system, we are going to discuss the Poisson effect. Okay. Yeah. Then we can extend it to a three-dimensional stress system also. Okay. The Poisson effect. What is meant by the Poisson effect? Let me define this Poisson effect. The deformation in direction perpendicular to the stress acting is called the Poisson effect. Okay. Let me explain that one. Let's take this kind of again certain sheet metal. This kind of forces are acting. Okay, forces are acting. Let's take the if force is acting on this stress element. Sheet metal. So then, due to act of this F force, what happened? This stretch. This component sheet metal is stretched in the force acting direction. While stretching, what happened in transverse direction to the force acting direction, it contracts. Is a normal behavior of a material. When this is stretched in force acting direction, it has a contraction in this direction. Okay, for any material, it's a normal way it deforms. And also same, if we this is for extraction, then what happens if the force is acting in inward to the considering element, considering sheet metal, what happens? It deform forming like this, no? Okay. Then it is contract in this direction, and also it is these dimensions are extend in this direction. Okay. This effect is called the Poisson effect. This effect is called the Poisson effect. Okay. Then this is a Poisson effect is depend on the material. The amount of contraction, amount of extraction is depend on the material. Okay, basically depend on the material. It's a material property. Okay, that amount of contraction, extraction due to the certain stress value is a material property that is measured by the Poisson ratio. Okay, let me explain that Poisson ratio. Poisson ratio, the symbol used is nu. Symbol used is the nu. Okay, actually there is a measure of Poisson effect for certain material. Then how to define this Poisson ratio? Actually, is a measure of Poisson effect for certain material. The absolute value of the ratio between the transverse strain to the axial strain is called the Poisson ratio. Okay, the new, we can write the equation according to the definition of the Poisson ratio. The absolute value of the ratio between the transverse strain in transverse direction divided by the strain in axial direction. Okay, axial direction, called a Poisson ratio. Why there's an absolute value? That why we are taking the absolute value in here? Okay, Poisson ratio we are defining with as a positive number. But here you can see. Here you can see when this component is stretched in this direction, there's a contraction in this direction. That means this strain, if we assign the coordinate system x and the y, strain in x direction is a positive, then strain in y direction is a negative. In here what happened, strain in x direction is negative, strain in y direction is a positive. You can see axial strain and transverse strain are in two different signs according to the two different situations. So that what can you say about this internal ratio? Always negative, no? The one, when one become positive, this one become negative, and when this one become positive, this one become negative. So the internal ratio always the negative. To make it a positive number, we are taken the absolute value. So other way, how to remove this absolute sign? In general mathematics knowledge, we are multiplying with the minus sign, no? Because internal ratio is negative, always negative. So strain in transverse direction divided by strain in axial direction. Okay, strain in axial direction. So that so then we can write strain in transverse direction. Strain in transverse direction is equal minus the new strain in axial direction. Okay, minus new strain in axial direction. Okay, then let's see how this transfers the Poisson effect in axial stress problem, the uniaxial stress problem. Let's take this kind of stress element is subjected to a uniaxial stresses sigma x. Okay, then let's assign the coordinate system also. X and the y. Then okay, then what is the strain in x direction? Let's take this, the material Poisson ratio is as the new. Okay, due to sigma x, what is the strain in x direction? We can simply say the sigma x divided by, if the material deform in a linear elastic region, we can say the sigma x divided by E. Then what is the strain in y direction? You can see this stretch in this direction, while stretching it is contract in other direction. So that according to this equation we can write minus the new epsilon x. Then this one we can further explain, minus new sigma x divided by E. This is the strain in y direction. This is the strain in y direction. Okay, this is the strain in y direction. So similarly, we can consider for biaxial stress system. Let's take the stresses acting in this kind of manner. Okay, this is sigma y stress, sigma y. This is how we are marking this stresses acting on this certain element. because these two stresses are in equal, sigma x and sigma y. This is the we are assuming this is the infinitely small stress element. So then these two are equal, in these two are also equal. So why these two are equal? Let me explain that one also. Let's take this kind of rope. Okay, this kind of rope. Then we are applying the certain force in this direction. Then we are applying the force in this direction. These two forces are equal. So then if we take a certain point on this rope, then from this point, here this is the point, this is the point, then what are the forces acting on this point? In this direction, a force. In this direction, a force. The equal and opposite forces acting on this point. No. Similarly, this is how we are marking the stresses acting on a certain element. Sigma x, sigma x, sigma and sigma y. Okay. Then the in opposite, these stresses are opposite in direction and equal in magnitude. Okay. Then let's take this so on a certain let's take the sheet metal. On a certain sheet metal, this kind of stresses are acting. So then due to act of these stresses, what is the strain in x direction? How we can calculate the strain in x direction? Strain in x direction. How we can calculate the strain in x direction? The due to sigma x, what is the strain? Due to sigma x divided by E. Then according to the in x direction, the due to sigma x is a stretch, but due to sigma y, there's a contraction in x direction due to the sigma y. That contraction is equal minus nu sigma y divided by E. Sigma y divided by E. That means strain in axial direction, strain in axial direction, the minus sign. Okay. So similarly, we can write the strain in y direction, sigma y divided by E. That mean stretch due to sigma y. The minus contraction due to transverse stress, this one, sigma x divided by E. This is for the biaxial stress system. How we can write the Poisson effect equations. Okay, Poisson effect equations. Okay, then what happen if the stress are in a three-dimensional system? For example, stress in three-dimensional system. Let's take this kind of three-dimensional stress system. Okay, three-dimensional stress system. In this direction, sigma x. In the opposite direction, sigma x. In this direction, sigma y. Sigma y. In this direction, sigma z. Sigma z. Okay. For this kind of system, you can see the three-dimensional stress element, infinitely small stress element. For example, if you consider certain body, is subjected to a three-dimensional force system. Okay, three-dimensional force system. Three-dimensional force system. If you take a cubical shape, infinitely small stress element from this body, the stresses acting on this considering element we can represent like this. Okay. Okay. Then let's assume only the normal stresses acting on it. Then strain in x direction for this system, we can write strain in x direction is equal sigma x divided by E. That is mean stretch due to sigma x. Then we have to subtract contraction due to sigma y divided by E, contraction due to sigma z divided by E. Okay. So similarly, we can write the strain in y direction. Sigma y divided by E. This is the stretch due to sigma y minus nu sigma x divided by E minus nu sigma z divided by E. Okay. Then similarly, we can write the equation for strain in z direction. Sigma z divided by E minus nu sigma x divided by E minus nu sigma y divided by E. These are the equations to find the strain in x direction, strain in y direction, strain in z direction under this kind of stress situations. Okay, I think you all got very clear idea about this Poisson ratio and the Poisson effect, Poisson ratio, and how we are calculating the strain in a different direction due to act of these stresses. Okay. Okay, then let's to understand this one, let's try to work out this sample problem. Let's understand further to this example problem. Okay, this is the problem we are going to discuss. Okay, this is the problem we are going to discuss. Okay, in this problem, strain gauges A and B. Here you can see the strain gauge. Here you can see the strain gauge A and B oriented in x direction and y directions respectively are attached to the rectangular aluminum plate with the thickness of the plate is given 7 mm. The plate is subjected to a uniform normal stress sigma x and sigma y, that is as shown in the figure, and the gauge reading for normal strain in x direction is equal minus 0.0075 and strain in y direction is equal 0.00125. The modulus of elasticity of the material also is given the 73 gigapascal, and the Poisson ratio of this material is given 0.33. Determine the following: the stress in x direction and the y direction we have to determine. The change in the thickness of the plate also we have to calculate. Okay, let's see how to calculate these things. Okay. Okay, let me draw the figure first. Okay, then let's take in this direction the sigma x, in this direction the sigma y is acting, then the thickness of the plate also given the 7 millimeter, and also the elastic modulus E is equal 73 gigapascal, and the Poisson ratio is given 0.33. Strain in x direction is given minus 0.00075. Strain in y direction is given 0.00125. Okay. Then we can write the equation based on this data. The strain in x direction is equal sigma x divided by E minus nu sigma y divided by E. Okay. Now what is the strain in x direction? Strain in x direction, that is given the minus 0.00075 is equal sigma x. What is sigma x? We have to find sigma x divided by 73 into 10 to the power of 9 minus 0.33 sigma y divided by 73 into 10 to the power of 9. Let's take this as the equation 1. Okay, equation 1. Okay, similarly we can write for this one strain in y direction. Strain in y direction is equal sigma y divided by E minus nu sigma x divided by E. Okay, 0.00125 is equal sigma x. sigma y. Sigma y we have to find. Sigma y 73 into 10 to the power of 9 minus 0.33 sigma x divided by 73 into 10 to the power of 9, that equation 2. You can see the two equations, the two unknowns, sigma x and sigma y are the two unknowns, the two equations. So then we can easily find the sigma x and sigma y. They're using the simultaneous equations. So I have already found that values. I like that one. Sigma x value I found that minus 27.648 into 10 to the power of 6 Pascal. Then the sigma y is equal 82.126 into 10 to the power of 6 Pascal. Okay, these are the two stress values. By solving this two simultaneous equation, you can see the two unknowns, two equations, so we can easily find the sigma x and sigma y. These are the two values for sigma x and sigma y. So then the problem also asking to find the contraction in z direction, no? That means the change in the thickness of the plane. So how to find the change in the thickness of the plane? That means to find the change in the thickness of the plane, we have to find the strain in z direction. If we know the strain in z direction, because z direction dimensions also known, 7 mm. If we know the strain in z direction, we can easily calculate the change in the thickness of the plate. Okay, let's see how to find strain in z direction. Okay, the strain in z direction is equal, you know, in z direction there's no any stress acting, but there how to find that one? I let the total equation, sigma z divided by E minus nu sigma x divided by E minus nu sigma y divided by E. Okay, sigma y divided by E. So then sigma z component is equal to 0, so that this equation can reduce to strain in z direction is equal to minus nu sigma x divided by E minus nu sigma y divided by E. Okay, so then I'm going to substitute these found values. Here is a negative sign, means it is acting inward to the stress element. Okay, so that means the compressive stress, the tensile stress, the compressive stress. Okay, compressive stress and the tensile stress. Okay, then let me substitute these values in this equation, then we can find the strain in z direction. Strain in z direction is equal Poisson ratio minus 0.33 sigma x. Sigma x with the sign you have to substitute 648 into 10 to the power of 6 divided by E. The elastic modulus of the material 73 into 10 to the power of 9 minus 0.33 sigma y, the 82.126 into 10 to the power of 6 divided by 73 into 10 to the power of 9. Okay, so then you can see we can strain in z direction we can easily calculate by simplifying this equation. I have already found that value. There is here it is negative, negative, positive, but here is a negative. That is equal to 0.2463 strain in z direction. If you know the strain in z direction, we can easily calculate the change in the dimension. You already know strain is equal delta L divided by original length. Delta L divided by the original length. That is the basic equation for certain strain. Here, what is strain? The minus 0.2463 delta L, change in the dimension, change in the thickness. So original length 7 millimeter. So then we can make delta L into subject by making the delta into L into subject. Here there's a 10 to the power of minus 3. Here also 10 to the power of minus 3. Okay. The 1.724 into 10 to the power of minus 3 in millimeters. Okay, 1.724 into 10 to the power of minus 3 millimeters. This is the change in the thickness due to this sigma x and sigma y acting on the plate. Okay, this is how we use this theory, the Poisson ratio, Poisson effect, when solving the problem. I think you all got a more clear idea. What is the Poisson ratio, the Poisson effect, and how that is affected to the deformation of the body. Then next we are going to discuss the sign convention used in the biaxial stress system. To represent the normal stresses, we are using the sigma. To represent the shearing stresses, we are using the tau. Okay. Then to represent the plane which is acting and the direction it is directing, we are using the two subscript letters. Something like that. Okay, something like that. So then the first subscript letter say in the direction. Direction. This one say in the direction. Direction it is acting. Direction it is acting. Then this one say in the plane it is acting. Plane it is acting. Plane it is acting. Okay, direction and the plane, the two subscript letters we are using. But in when expressing this normal stresses, you can see the two subscript letters are repeating. So we are using, instead of the repeating the two subscript letters in the biaxial stress system, these two are repeating. So instead of using these two subscript letters, we are using the single subscript letter sigma x, and for the sigma y. Okay. Then the tau xy, then the tau yx we are using for a biaxial stress system. Okay, let me explain that one further. Okay, then let's take the two-dimensional stress element. Let's take this the two-dimensional stress element in a biaxial stress system. Okay, x and the y, these are the coordinate system with reference to the biaxial stress system. Then these phases we are called it as a positive phases. These phases we are called it as a positive phases. These are called positive phases. These are called negative phase. So what is the phase? Let's assume it has a certain thickness. Okay, let's take this dimension element having a certain thickness. The phase means this phase. This is the phase. Okay, this is the phase. Then the bottom there's also phase. In here also there's also phase. This phase we are called it as a positive phase. Why is called the positive phase? Because it is normal to the positive coordinate directions. That means this x phase is a positive phase, positive x phase. That means it is directed normal to the positive x coordinate direction. And also this is a positive y phase. That is called y. That is why it's called positive y phase, because it is normal to the positive y coordinate direction, y coordinate axis. Okay. Then these are negative phases. Why is called negative phases? It is normal to the negative y coordinate axis. Then this is also a negative x plane. Why is called? It is normal to the negative x coordinate axis. Okay. I think you all got a more clear idea what is in the positive phase and the negative phases. Okay. Okay. Then let's see how to mark stress, positive stress positive normal stress. Okay, if the normal stress acting outward from the stress element, we are taken as the positive. Okay, when marking the considering plane, if the for any plane, if the stress normal stress are acting outward from the considering stress element, we are taken as the positive. Okay, that means this is the positive way we are marking the stresses. So sigma y, sigma x, sigma y. Okay, you can see on this face, that means the stress acting on this face, we are marking in a positive way, we are marking sigma x outward, sigma y outward. Okay, then these two stresses are equal in magnitude and opposite in direction. Sigma y also equal in magnitude, opposite in direction. This is because this is the infinitely small stress element. Infinitely small stress element. Okay, then if not, if it is not infinitely small, if it is in the finite dimension, these two may not equal. Okay, then yeah, this how, yeah, let's take the example. Let's take the sigma x is equal minus 10 megapascal, then sigma y is equal 10 megapascal. Then how to mark these stresses on a two-dimensional stress element in according to the sign convention of the normal stress. Okay, let's take this kind of stress element. This is the stress element we are going to mark. These are the coordinate system for this stress element. The sigma is negative 10 megapascal. That means this is how we are marking that one. Minus 10 megapascal. Minus 10 megapascal. Here, what is that value? The 10 megapascal. This is how we are marking the stresses according to the sign convention. Or we can use this way to mark this one. Instead of marking the outward, you can mark in this way. Now it's 10 megapascal. 10 megapascal. Here it is outward 10 megapascal. 10 megapascal. Okay, the both are correct. Both are correct. Then now you know how to mark the normal stresses on a two-dimensional stress element. Let's see how to mark the shearing stress on a two-dimensional stress element. Okay, two-dimensional stress element. Okay, if the shearing stress acting on a positive plane and it is directed to the positive coordinate direction, we are taken as a positive shearing stress. That means if the shearing stress acting on a positive plane, okay, what are the two positive planes? This one is a positive plane according to the coordinate system. This one is positive, this one also positive, this one negative, this one negative. If considering shearing stress acting on a positive plane and it is directed to the positive coordinate axis direction, that means this kind of stress, you can see tau x y. The first subscript letter saying the direction, it is acting y direction. It is acting y direction. Then the plane, x plane. These are called the x plane. X, positive x plane, positive y plane, negative y plane, negative x plane. Okay, these are called x plane. That's why the second subscript letter plane. Okay, then this is how we are marking the positive tau xy. That means shearing stress. That means stress acting on this plane is a considering plane that is acting in this direction. Let me draw it very clearly. Let's assume it having this kind of finite dimension. Okay, this is the stress acting tau xy we are marking. Okay, we are marking. Okay, then Similarly, we can mark this stress acting in this one, tau yx. In this time you can see the plane, it is directed x coordinate direction, and also it is acting on a y plane. This is the y plane, these are y plane, these are y plane. Okay, then similarly we can mark the stresses acting on these faces as also, tau yx, tau xy. The x mean it is acting negative x coordinate direction, and also it is acting on a negative phase. Here it is acting negative y direction, direction is y, then it is acting on a x plane, that's why the yx. Okay, this is how when the shearing stress is acting on a negative direction, a negative phase, and it is directed to the negative coordinate direction, then we have taken this shearing stress as positive. Okay, here negative, and also it is directed to negative direction, negative become positive. You can think, you can remember that way. Okay, negative when multiply the negative, it become positive. In that way you can remember that concept. Okay, then here also we can mark that one, tau yx, then here tau xy, tau yx. Okay, tau yx. Similarly, we can say that these two are unequal in magnitude. That means the tau xy and its magnitude tau yx, considering the rotational equilibrium of this stress element, the magnitude of these two are equal. Okay, then I think you got a more clear idea how to mark the shearing stresses on a two-dimensional stress element. Okay, then let's see how to mark the stresses on all of these plane. You can see normal to the coordinate axes. Okay, this plane and this plane, all the four faces are normal to any of the coordinate axes. Then what happen if when you are going to mark the stresses on an inclined plane? For example, if we split this stress element in on this plane, then we are having this kind of triangular shape stress element, no? Then in that way, how to mark stresses on this kind of triangular shape stress element, next we are going to discuss. The stress, the sign convention when marking the stresses acting on a inclined plane. Okay, stress acting on a inclined plane. Okay, this is our coordinate system, x and the y. You can see this plane has inclined at an angle theta to the x coordinate direction. Okay, x coordinate direction. No matter this how you mark these stresses, sigma y, sigma x, tau yx, tau xy. And how to mark stress acting on this plane, inclined plane? How to mark stress acting on this inclined plane? Same for the normal stress. If the considering normal stress acting outward from the considering plane, we are taken as the positive. This is sigma theta. This is the positive way we are marking the sigma theta. And also, if the acting shearing stress tends to rotate the stress element in anti-clockwise direction, we are taken as positive. Okay, anti-clockwise direction to the plane, we are taken as positive. This is the way we are marking. This is the sign convention we are using biaxial stress system to mark the stresses on a stress element. Okay, so for example, let's take example. Then sigma x is equal minus 5 megapascal. Then sigma y is equal 10 megapascal. Tau xy is equal minus 7 megapascal. Then how to mark this one? Okay, on a stress element. Let me draw the stress element. Okay, how to mark this one on a stress element? You can see this -5, -5, it is 10, here it is 10, it's a -7, no? 7, -7, -7, -7. Because all of these force shearing stress are equal. Okay, so then this is how we are marking this stress. Similarly, similar one we can draw this one, eliminate in the negative signs. This is acting inward 5, this is acting inward 5, outward 10, outward 10, seven, this is 7. Okay, they both are correct. Here the stress, we have changed the direction is acting, so that they then it become positive. Okay, then here also we change the direction it is acting inward to the stress element. Those are negative values, so no need to put the negative sign in here, because we have already represent as a negative stress. Here also we have represent it as a negative stress. So this is how we are using, this is how we are marking the shearing stress and the normal stress acting on normal phases and also the inclined phases in a biaxial stress system. I think you all got very clear idea how to mark these stresses on a biaxial stress element. Okay. Okay, then let's move to finding the stress on an inclined plane. Okay. For example, let's take. For example, let's take this is the sheet metal. It is subjected to a this kind of distributed loads. Okay, distributed load. So then stress acting on this. Let's take let's take infinitely small stress element. The stress acting on this infinitely small stress element we can represent. Okay, and also let's take it is also subjected to a shearing forces also, shear forces also, shear forces also, shear forces also. So then stress acting on this element we can represent by this kind of manner: sigma x, sigma x, sigma y, sigma y, and also the tau xy we can represent like this. Okay, then we are interesting about the stress acting on this kind of inclined plane. What is the stress acting if we split, if we produce a certain line on this sheet metal, then what is the stress acting on this considering plane? Okay, then what are the normal stress, and also what are the shear stress acting on this tau theta acting on this plane. Okay, then that means this is the taken stress element, then this is the considered point, then we are split this stress element in a diagonal along the diagonal line. So then we are having this kind of stress element, triangular shape stress element. So what are the stress acting on? Sigma y, in this direction sigma x, then tau yx, tau xy, then stress acting on this plane. Okay, when isolating from this side, that means we are going to represent free body diagram for this separated part. So then stress acting on this plane, we can represent is still unknown sigma theta and tau theta like this. According to the positive sign convention, we are marking these stresses. Okay. On this plane also certain stresses are acting. That is stress is equal tau theta and sigma theta. It's still unknown. Then let's take we know these stresses. Then let's see how to find these two unknown stresses. Okay. Okay. Then let's see how to find these stresses. Okay. Then next we are going to discuss how to find the stress on an inclined plane. Let me draw the coordinate system. X and the Y. Let's take the triangular shape stress element. Li equal to the area I explained. Within in this sorry, let me take another color. Sigma Y, sigma X, and also the shear stresses. Tau Yx, tau xy, and also the inclined plane stresses I am going to mark. Sigma theta along the plane, shearing stress tau theta. The inclined angle to the anti-clockwise direction to the positive x coordinate direction is figured as theta. Theta always measured anti-clockwise from the positive x coordinate direction. Okay, so then these are the data given. Then these are known: sigma x, tau xy, tau yx, and sigma y, and also the theta also known. So from these known values, we are going to find the sigma tau theta and the sigma theta. Okay. Then how we are going to find this one? We are going to consider the equilibrium of this is considering stress element. The force equilibrium we are going to consider. Okay. That means I am going to resolve the forces perpendicular to the VC. That means let me assign the numbers for this one, A, B, C. Okay. Resolving the forces. Perpendicular to the BC. Okay. I am going to resolve the forces perpendicular to the BC. Okay. Then what are the forces? Okay, let me draw that one also. Here, this angle also. Okay, this angle also theta. This angle also theta. Then this angle theta. Then this one is theta. This one is theta. Okay. Okay. The resolving the forces perpendicular to the BC. Let's assume this one having the thickness T. Okay, this one having the thickness T. The stress element having the thickness T. Okay, then let's resolve the forces. So then what are the force acting on the BC plane due to the sigma theta? Area into stress. What is the area? BC into thickness of the considering element. Okay. Okay, that means we are considering this kind of element. Okay, this kind of element we are considering. That means this thickness as T. Okay, then the sigma theta acting normal to the plane, sigma theta, then force into stress into area. We are able to calculate the force BC into T into sigma theta. Similarly, there's no because we are resolving perpendicular to the BC plane. There's no force component from the tau theta because it is perpendicular to the resolving direction. So then the minus AB. Let's move to this plane. minus AB into T, the sigma y, this direction sin theta, sigma y sin theta. Same time for the tau shearing stress component T, tau yx cos theta. Then that is also negative direction. Yeah. Here also negative. No? AC into T into sigma x cos theta. No? Cos theta minus shear component AC into T into tau xy sin theta. Sin theta is equal to 0. Okay. Sin theta is equal to 0. Okay. Then we can cut T. The T is a common term. The T we can cut. At the same time, I am going to make sigma theta into subject by dividing the BC. Okay. Then we are having sigma theta is equal AB divided by BC into sigma y sin theta plus AB divided by BC tau xy cos theta plus AC divided by BC sigma x cos theta plus AC divided by BC tau xy sin theta. Okay, tau xy sin theta. Okay, then what is meant by this AB divided by BC? AB divided by BC, according to this ABC triangle, this is theta. AB divided by BC is equal sin theta. Okay, that means this equation again right, sigma theta is equal sin theta into sin theta sin square theta, sigma y sin square theta plus AB divided by BC, AB divided by BC, again the sin theta, tau xy sin theta cos theta plus AC divided by BC. AC divided by BC means the cos theta, cos square theta into sigma x plus here also cos theta tau, sorry, here is tau yx, no, yx tau xy sin theta cos theta, sin theta cos theta. Here you can see the tau yx is equal tau xy in magnitude. So instead of I'm going to tau yx, I'm going to put the tau xy. Within this equation, sigma theta we can write, okay, sigma x cos square theta plus sigma y sin square theta plus 2 tau xy sin theta cos theta. Okay, this is the equation. This is the final equation we can use to calculate the normal stress acting on an inclined plane in a biaxial stress system. Okay, that means by substituting the relevant theta value in this equation, the sigma x is known, sigma y also known, tau xy is known. Then by substituting the relevant theta value, then we can find the sigma theta. Okay, sigma theta. Then similarly, let's see how to find the tau theta. So then I am going to resolve the forces in BC direction. Forces in direction the BC, in direction BC, we are going to resolve. Okay, then what are the forces? Tau theta the BC into T. Okay, tau theta BC into T. If we take the sigma x component in this direction we have to resolve. Okay, this one is equal to theta, then this is 90 minus, this one is theta, this one also theta. Okay, tau theta BC into T, then if we take this one, the plus sigma x into AC into T into sin theta, no? Sin theta minus tau xy AC into T into cos theta, then minus sigma y because it is acting in the direction, the T into AB cos theta plus shear component AB into T into tau yx into sin theta. Sin theta is equal to 0. Okay, then we can cut T. It's a common term, we can cut the T. So this one. At the same time I am going to divide by the BC and making the tau theta into something. Okay, the BC I am going to divide, we have taken the side minus sigma x AC divided by plus tau xy AC divided by BC into cos theta plus sigma y AB divided by BC into cos theta plus AB divided by BC tau yx into sin theta. Here it is negative, no? This one negative, this one negative. Then tau theta is equal here minus sigma x sin theta AC divided by BC according to the diagram. AC divided by BC is a cos theta, sin theta cos theta plus tau xy AC divided by cos theta cos square theta plus sigma y AB divided by BC. AB divided by BC means sin theta cos theta minus AB divided by BC sin theta tau yx sin square theta. Okay, then we can write the tau theta by making minus sigma x minus sigma y divided by 2 by writing the sin theta cos theta in 2 theta angles. Sin 2 theta, you can see tau xy is equal to tau yx in magnitude, so I am going to put only tau xy. Cos square theta minus sin square theta mean cos 2 theta. This is the final equation for tau theta. Okay, these are the two equations we can use to find the stress on an inclined plane. Okay, the here sigma x known, sigma y known, tau xy known, theta is known, then we can find the sigma theta. Okay, for any inclined plane, for any inclined direction, we can find normal stress and the shear stress acting using these two equations. Okay, using these two equations. Okay, let's understand this use of this equation through the example. Okay. Okay, this is the example we are going to discuss. The stress acting on an element within the structure is given this way. They determine the stress on the element if it is rotated by a counterclockwise by the 30 degree. Okay, that means stress acting on a 30-degree inclination angle we have to find. Okay, let's see how to do this problem. Okay, let me draw the figure first. See the figure. Then sigma x is equal minus 50 megapascal. Sigma y is equal 30 megapascal. Tau xy is equal 10 megapascal. Okay. Then the problem is asked if the stress element. Let me draw the coordinate frame also. This is our coordinate frame x and the y. If you rotate this stress element clockwise and counterclockwise by 30 degree, that means if you rotate this stress element something like in this kind of orientation, okay, that means this face (30°). Then what are the stresses acting on this constituent plane? Problem is asking. Okay, problem is asking. Then how to find that one? Actually, we are finding stress sigma theta and the tau theta for inclined angle 30°. Okay, if we know the stress acting on this face, other faces we can easily mark. Okay. Okay. For this plane, it's a angle theta is equal 30. For this plane, this inclination angle is equal this total angle 90 plus 30°. 90 plus 30°. Okay, let's see how to solve this problem. Okay. So first of all, I'm going to use this equation, obtain equations to find sigma theta. Sigma theta is equal to 30°. What is the obtained equation? Yeah. Sorry. First of all, I will write the obtained equation. Sigma x cos square theta plus sigma y sin square theta plus 2 tau xy sin theta cos theta. Now sigma 30°, sigma x, what is sigma x? Minus 50. With the sign you have to substitute the values. Cos square 30° plus sigma y is equal 30 sin square 30° plus 2 tau xy mean the 10, no, 10 sin 30 and the cos 30°. Okay, you can see by solving this equation the sigma 30° we can calculate. We will get the answer. I already calculated that one. That is equal to 31.3 megapascal. Okay, stress acting on this, normal stress acting on this plane. Okay, then the shearing stress, sorry, tau theta, what is the equation? Minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cos 2 theta. Okay, then the tau theta is equal minus sigma x minus 50 minus 30 divided by 2 sine 60 degree plus tau xy 10 cos 60 degree. Then tau theta will get the answer 39.6 megapascal. 39.6 megapascal. Okay, 39.6 megapascal. Okay, then similarly you can by substituting the 90 plus 30 in this equation, we will get stress acting in this plane, that is equal to is equal to 48.7. Okay, stress acting on this plane by substituting the sigma 120, that is equal to, I have already calculated the value, the 48.7. Okay, so then how we can mark all of these stresses on a stress element, the found values we can mark in this way. Okay, then normal stress, what is the normal stress acting on it, we have found already, found the value is equal minus 31.3 megapascal. In this direction also same, minus 31.3 megapascal. Then I have found this value, that is equal to 48.7. Sorry, this one should be 111.3. This one should be 111.3 megapascal. So this one should be corrected as 111.3. Okay, keep remember that one. Then what are the shearing stresses? Shearing stress, that is equal to 39.6. This is our coordinate frame. Then this is how we are marking all the inclined stresses acting on this plane using the obtained equations. Okay, and this is all about the theory related to the biaxial stress system. On the next day class, we are going to discuss how here we have found the, in this equation you can see there is a theta is the variable, no? Theta is the variable. By varying, we have obtained the different sigma value, normal stress value for this biaxial stress system. On the next day class, we are going to find the maximum sigma theta maximum value and sigma theta minimum value, and tau theta same maximum value and tau theta minimum value. Okay. Okay, let's continue next day class. Thank you.